Who here likes math? Okay, good. So we're going to talk about math. So my talk is sculpting and drawing with algorithms using WebGL. And so just to kind of get started, I'll tell you a little bit about myself. So I'm an art major. I studied sculpture, contemporary sculpture in school. And got into graphic design and working on exhibits for aquariums and stuff. And then I decided, you know what, I kind of like this technical stuff. So I moved to doing creative work with an agency, doing web development. And after that, I was like, you know what, I really like nerdy stuff, so let's get into browser engineering. So I started working at Mozilla, working on developer tools. So I work on different things to help make Firefox faster. So the stuff that Mozilla pays me to do is not particularly crazy graphics stuff, making things fly across the screen, which is what I'm going to talk about. But it's a passion for me, and it's something that with my path to get to where I am has extremely influenced how I got to what I'm doing right now. So going into interviews, it's fun talking about ray marching algorithms or something crazy with graphics. And so hopefully I can show you a little bit about like what I'm passionate about and get you just a little bit excited about graphics programming, and specifically graphics programming on the web. So about a little over a year ago, I started a project of making graphics on a web page. And kind of, I wanted to make art with restrictions. And part of that was to use no Photoshop, no graphics programs, just code and math to generate everything. And this creates a sense of focus and challenge that I think is really nice for creativity, because a lot of the creative process is about defining restrictions and seeing what you can do with those restrictions. So we're going to go through a little bit of that. I'm glad everyone raised their hands about being excited about math. I don't always get that response. But this is about getting a feel for the process. You don't have to understand the math. And we're going to hand wave over details. One thing that I find is that math really takes effort to learn. It's hard. You have to really think. A lot of times it doesn't make sense until you really struggle with it. But after you do that, math can be really fun to use and really empowering with what you can build for it. So with that, we'll get to demo time. I hope you all want some things flying across the screen, because that's what we're going to do. So to start with, I'm going to show you like a few things that I've built using, so this is running in the browser, and it's pretty much just using math and geometry to create visuals. And this is all real time, not pre-generated, so it's kind of crazy what browsers can do now. And so these are all like experiments that I've been playing with at night usually. Usually, I've been programming all day, and I'm like, oh, what do I want to do when I get home? Okay, like put the kids to bed. Time to program some more. Okay, but it's a different type of experience going through and building things and saying, oh, I wonder what happens if I do this. If I can create this type of geometry, if I can make it do something on the screen, what can I do to kind of visually express these different ideas? And I can make like creepy, weird little mask guys, and there's like no model here. It's all just procedurally generated, so it's lots of fun, and actually I like this one a lot. And it's funny because like it takes like 2 or 3 seconds to load, or actually less than that. I have a new computer, so it's faster. But it's actually having to generate all the geometry on the fly in the browser, so it does actually have to do some non-trivial work to do that. So how do we do that? Let's start with just a little bit of code. So I like to do ASCII art because I can put it in version control. And so this is how I define geometry. You have a triangle, which is kind of the base unit that you're going to be that you typically work with. And you have points A, B, and C. And so what that looks like, and this is JavaScript, is you're going to have an array of positions with point A, B, and C defined, and they're just like little small arrays. And then you're going to have a cell, which is an index into those positions. And so this would be like how I would define a single triangle. If I want to define more triangles, I add more data here. And so if I'm going to start using code to generate this, I'm going to start to target this type of data structure. And I have this little hand-wavy thing. Don't look too closely at this. But this code just basically says, OK, let's create some buffers. So this is raw binary data that we can then throw to the graphics card to do the work. And ultimately, I'm just going to return the positions, and then I'm going to call the cells elements. So it's triangle data and how those triangles are put together. Those are like the two things. And finally, we're doing WebGL. So WebGL, if you like reading specs, who likes reading specs? Yes, there's a few of you. I love reading specs. They're so much fun. I love reading them because they let you like really know how to implement something. But doing them for fun, just like on a side project, that's not great. So I use this framework called Regal, which is sort of like React, but for WebGL. It lets me define my shaders, which shaders run on the graphics card. And I can throw tons of triangle data at it, just like tons of data, and it processes it all in parallel on the graphics card. So this code shows that I can use Regal, so it's like creating a React component. And I give it a vertex shader, which is source code that can move a vertex around, and a fragment shader, which will generate a pixel fragment, so just a single pixel. And this is all done in parallel, and I can pass in even more data, so my attributes. So, okay, I've got the little hand wave emoji again, so there's some math ahead, but I still want to show it, just because even if, just like wave over don't look at the details too much. But I have two for loops, and those two for loops build two triangles, triangle A and triangle B, and I generate the X and Z components of each of those and put them together. So here's a tiny bit of math. Like, this is not crazy math. It's just like doing a little bit of multiplication to move around. And I define two triangles, and I push those on. And this one, there's no indexes. It's just a list of triangles. So what's crazy is in the browser now. So on the left side of the screen is a browser tab. And I have a shader written in a C-like language called GLSL. And the browser takes that file from the random person on the internet and compiles out of the browser, and then runs the code. So that's like terrifying and awesome. This void main function is going to generate a new position for every single vertex. So every single vertex in massively parallel code gets run. So what I'm going to do is show how I can start to modify that. So I'm going to take my new position, and I'm going to take the y parameter. So this is y is up and down. And I'm going to set it to 0.5, let's say. And you see on the left, it's moved. And so I can keep on moving it and change the value across the screen. So you can see I can start to programmatically take this data and play around with it. OK, well, that's boring, just setting a single value. But I have uniform values that are uniform across everything. And one is the current time in seconds. So if I take that, I can make it fly across the screen. OK, so let's try to keep that on the screen. There's this nice math function that I like to use that can move up and down, and that's sine. So if I run time through a sine function, now we can see that the geometry is moving up and down. So now I can start to think mathematically about my data and think about functions and how I can take that and change it. Now, time is a scalar value, so I can scale that value up or down. So if I want to make it move faster, let's multiply by 5. OK, now it's moving fast. OK, I don't know, 100. Yeah, too fast. So I'm going to find, yeah, 3 looks nice. And it's kind of moving really high. It's kind of moving off the screen. That's not too much fun. So let's make it move a little bit lower. So we're going to multiply the ultimate value by, I don't know, 0.3. OK, now we've kind of got a warbling vertex. But we're not differentiating across every single position. And this is in parallel, so I can't ask, like, where are all the other positions? I can only look at the current one. So in order to change how this looks, what I'm going to do is take the position dot x parameter and then add that to the time. So you can see it's starting to wave sort of like a flag because each position is offset a little bit into the sine function. So if I start adding and making that like a little bit closer together, you see now it's waving more and more and more. So as I'm done with my day, put the kids to bed, I want to play around, it's like, oh, sine functions, these are so much fun. And you can do weird stuff, like, okay, let's put time into here as a parameter. So this will slowly start to wave faster and faster and faster, which I can do it faster than that. Let's multiply that by 3. So you can see this will take all of our positions and make them more and more kind of compressed together. So for my next trick, we've done one dimension. So everyone likes to talk about multiple dimensions stuff. Oh. So we'll duplicate that, but instead of position.x, we'll do position.z. So now we're doing that across both the x-axis and the z-axis, because remember, y is up and down. So we can start to get kind of like an interesting form that's happening. And let's make that a little bit more dramatic. Okay, you can kind of see what's going on, but right now everything's red. So it's hard to differentiate between the different things. So if I go down a little bit, I've got a fragment shader defined here. And again, this is just text code that gets compiled to a shader. And ultimately, this void main here is the main function, and I have to set the fragment color. And a fragment's a pixel. So I've got red, green, blue, alpha, and it's ranged between 0 and 1. So if I set the blue color, you can see it turns like a magenta. I can do my time trick or my sign of the time trick. So now it'll go between different colors. But what I want to do is take a value that varies between everything. So varying means like I have lots of different vertices, and I go down to a pixel. So I want to be able to pull my vertex information down to my fragment, which I have not defined this yet. So we'll set our v position to our new position, and that'll get pulled down to our fragment shader. And I can start playing around with that. So we'll set our blue color to the v position dot, let's choose dot y. And let's actually do that as the red color so that we can start to see it. So I've taken a value that ranges between certain different values, and the higher it is, the brighter red it's going to be. Which is a little dark still, so let's make that more dramatic and maybe add a little bit. So there's all these magic values that end up creeping in throughout the code. So normally when I'm writing something for real, I name all these things, but I don't have time for that right now. So we've just got red. Let's spice it up a little bit. And do, oh yay, multicolored things flying across the screen. I told you I'd make things fly. There we go. And then, just for fun, let's play with these values so we can see how we can start to change it. So, as I'm exploring some of these functions, like the sine function is fairly simple. It moves up and down. So when I view it, you can like compose them together and create waves and different things. But it becomes a way to intuitively start to understand what some of these functions are doing. So you can visually play with it. It becomes something that's a lot less abstract and much more concrete because I can change a value and see how it's reflected in my code. Okay, that was a plane which is kind of 2 dimensions, and then we kind of played around with it and translated it into 3 dimensions. Let's take this idea and start to find a way to sculpt our values. So I've set up this new program to not use triangles, but use quads. So quads are defined as 4 points, A, B, C, and D. And when I actually pack that into a buffer, I just pack it into triangles. So it goes from 4 points to 2 triangles. And it has this nice property because I can actually take that and then start to subdivide it. There's this nice algorithm that someone wrote research papers on, and someone else implemented, and I downloaded from the internet. It's called Catmull-Clark subdivision. I'm sure they're nice folks. And I can start to subdivide that mesh. And so it gives me a way to define squares. So squares, I can take a piece of paper and start to draw squares out and think about how I want to work with those. And not only that, I encode all my information in ASCII art, because ASCII art is so much fun. I love ASCII art. I love specs, I love math, I love ASCII art. Let me hear, hold on. So let's comment this back out. And I've written this function called extrude, which takes a single quad, which we're going to call cell in this instance, and it extrudes it out like a pasta extruder. And so I've defined this function, but I don't have all the words defined yet. So if I save this, I'm going to get some errors that says cell is not defined. Okay, so let's start defining all these things. So cell, let's take our mesh cells and pull out the first one randomly. Now we have inset percentage, it's not defined, so inset percentage, 0.5. And extrude length, I don't know, random numbers. Okay, so we've extruded it out a bit, and now like the top quad is kind of off the screen. That's hard to see. Let's adjust the size a little bit down, playing with magic numbers. And then the length is still really long. 0.5. I always play with magic numbers with orders of magnitude to get them in the range, because I don't know what it's going to be. It's just some random number. So I've extruded one thing. So we're starting to see kind of interesting effect, but this is programming. What can we do with programming? Well, loops are nice. We all write loops. So let's do this multiple times. So I'll do a for loop with, let's say, I don't know, 10. We'll go high. And then we'll take our little function here and put it right inside that for loop and see if it still runs. Okay, it's off the screen again, so let's, oops, wrong way. And then the length is probably too long. Okay, so now we have, it's like, okay, Greg, we've taken a box, and we made it like extrude out. This is weird. What can we do next? Well, we've only done one of the cells on the box, so let's play with that. I guess I could do, oops. Let's take this one, go through each of those cells that are in the mesh, and then let's run it on a loop. Now we've got a weird star shape. Let's push it a little bit further. Oh, and we haven't looked at what it looks like whenever we run our nice little smoothing algorithm to subdivide on it. So now that smooths it out a little bit. So we've got this weird diamond shape. But I think I can make this more organic looking. So I'm going to take this subdivide, and I'm going to put it up here and put one in. Okay. So we're making it a little bit more fun. So with this step, you can see like how I've taken something that's just like, okay, I'm going to build some kind of library to work with boxes. I've taken someone's algorithm I looked at online and start to implement interesting things with it. And going back to my examples, this is actually the code that led to this example right here. You can see now how I started to generate this. I can take each step that I did and move it around just to like a little bit to play with it and see what I can generate with it. And thinking in terms of like artistic expression, I can start to generate some background, a little dust to make it look like it's kind of organic and microscopic. So these are all just become tools that I can play with. And when I start out, I don't start out with the crazy 3D stuff. Most of the time when you start out with graphics programming, you start out in 2D and start out with something simple, like drawing rectangles. So I'm going to do a quick plug for a side project because I have an audience and I can do that. So I'm working on I like this idea of art with restrictions. So I'm building this like little CodePen-like project called Glitter, because I got glitter.io. That's a cool domain name. And I can start doing this creative coding just in the browser and play around with it. So here I've got a function that generates, that draws just rectangles. And let's see, I've got like 5 minutes if I can do this. I wrote this function random point on a sphere, and it's pointing to like a Wolfram page, just defining how that's like the math works on that. But I've got all these magic values. You can kind of see. Oops, I don't save on this one. It updates live in the browser, and then I can go in, and rather than generate kind of this random square point, I can generate something on a sphere and move it around. And I'm drawing this is 2D. There's no like, this is not WebGL. This is 2D canvas. I'm just drawing a rectangle. But even though all I have for what I can do is drawing rectangles, you can do a lot with this. So let's do more points. And I have a loop function that lets me draw these things in a loop. And so my ultimate function of the drawing is this rectangle. So rectangle takes a white color and draws it at this position and at this width. So here's this width. There's, drawing it 1,000 wide, but we're just doing 4 pixels wide. So let's play with this. Here's another link to some more math about a rotation matrix. If you're doing graphics programming, matrices are a great way to transform your data. So here's a simple 2D rotation. And if you notice, these cosine and sine variables sneak in. Let's see if I can make that a little bigger. So let's see if we can rotate. So we're going to rotate the x and y. Oh, let's not center. We'll rotate the x and y by the current time. Okay, that's just the x-axis. Then I have this rotate y. Okay, this is fun. So this is still 2D. It feels very 2D. But I can take another parameter. I actually did generate the z coordinate. And it's just data. It's not anything magical. It's another dimension, but hey, that sounds like sci-fi. So if I just rotate the x, I can start to make this start to feel like a three-dimensional object, even though I'm still just drawing rectangles right now. And you can take these like small restrictions of just drawing a rectangle and use math and use kind of creativity to generate things. And of course, I've got that. There we go. Plugged it. Let's move on. So getting into graphics, and this is more about side projects. And kind of on my closing note, what I'd like to say is having a side project and being passionate about something. I get the question a lot, like, well, what's it useful for? I'm like, I don't care. It's just fun. I can give you reasons why it's useful. Like, it's been helpful in my career path to have developed a lot of these skills. So there's things that come in handy, but really it's about being passionate about what you're working on. And so if you want to get into any type of graphics work, I have kind of a few quick pieces of advice. Be prolific, throw stuff away, just build a lot of stuff, fail, and move on. If you want to do graphics, learn 2D first. Multiple dimensions are hard, do the easy problem first. And don't overinvest in a big project like a monolithic game. So on side projects, you have a little bit of time in the evenings or like on the weekend at a coffee shop. Just like play with something and be prolific with it. I'm online. I've got my website at gregtatum.com. All my stuff's open source, so please like check it out. I've got like some other things on there. Thank you all so much.